It looks like it's about time for us to get started. Thank you all for coming today. It's my honor to introduce Peyam Tabrizian from Brown University, talking on the factoring method that will change your life.
All right, so let me just share my screen. Here we go. All right, so let's get this ODE party started. So hello, everyone, and welcome to the factoring method that will change your life. And just a little disclaimer, I did not come up with this method, but I feel it's not talked about enough. And I feel this should be the way you should teach ODEs. Now, let's talk about our culprit. So y double prime minus 5y prime plus 6y equals 0. And let me know if you're guilty of teaching it the following way. You guess that the solution is of the form e to the RT, which already leaves the student confused. They're like, why e to the RT? And usually your answer is, well, because it was done with first order ODEs, which is not very satisfying. Okay, and then you plug it into the differential equation, and you eventually find r equals 2 and r equals 3, which means e to the 2t and e to the 3t are solutions. Okay, that part is okay. But then you come out with that Wronskian, and you find the Wronskian is non-zero, which, again, leaves the student very confused. And then you conclude that y is ae to the 2t plus be to the 3t, which in the end just leaves the student crying because it just seems there are a lot of steps that are unmotivated. And the question is there a more direct way? Is there a way to go from the differential equation y double prime minus 5y prime plus 6y equals 0 to ae to the 2t plus be to the 3t? And the good news is, yes, there is. And this is the one I want to talk about today. And little disclaimer, so this video, this idea is featured on my YouTube channel, which currently has actually not 161,000 subscribers, but now 163,000 subscribers and close to 1,000 videos. And in fact, I presented it in that video in, I think, the cool method that will change your life, and it has 110,000 views. So I think a couple of people are pretty interested in it. Okay, now let's not beat around the bush. Let me tell you how it works. So it's based on a more dynamic perspective called differential operators. And it's just another way of writing derivative. So when I write dy, it is y prime. But the nice thing is this is more the action of the derivative applied to the function y. And of course, you can do it twice. If you do d dy, by composition, it is y double prime. And last but not least, the identity just does nothing. I of y equals y. And the cool thing is, using just this notation, you can write your ODE in a more dynamic perspective. And in fact, let's do that. So let's start with our culprit again. Y double prime minus 5y prime plus 6y equals 0. But in terms of our notation, this becomes d squared y minus 5dy plus 6iy. And the cool thing is now we can see that the y sort of factors out. So this is really the same thing as saying differentiate y twice, subtract 5 times the derivative of y, and do 6 times nothing. And this thing we can now factor out, the expression turquoise. So in fact, if you factor this out, you get d minus 2i times d minus 3i. And you can check using the definition that this is legit. And the cool thing is, what this does, it actually turns the second order ODE into 2 first order ones. Because the thing on the right, you can just call it z. Again, just some notation. And what happens to the ODE, it then becomes d minus 2i z equals 0. And using the definition, this just becomes z prime minus 2z equals 0. And now we're back to first order ODEs. So this is the one we're happy with, sort of our happy place. And we get z is ae to the 2t. And we just need to unwind this using the definition of z, because z is just d minus 3iy is ae to the 2t. And then we just get a first order ODE, which now we can solve using integrating factors. So you see already, you can see the nice thing is it's very direct, and it turns the second order ODE into two first order ones. So let's just finish this up. The integrating factor is e to the minus 3t, which turns this into the product rule. So e to the minus 3ty prime is ae to the minus t. Then you integrate, and you get e to the minus 3ty is minus ae to the minus t plus some constant. And last but not least, you multiply by e to the 3t, and you do get your solution. So remember, a is arbitrary, so is minus a. So in fact, just starting from first principles, you go from the ODE to the solution, which is generally what we want. So once again, to recap, by factoring out the ODE, we directly went from the ODE to the solution, which is what we want. So you see, this is a really cool and direct method. And what I'll show you in the next couple of examples is that it's super flexible. You can literally apply it to sort of any constant coefficient second order ODE and more, in fact. But I do want to stop for a second talking about the pros and cons, because there's a good way to use this, but also there's some drawbacks. Okay. So the pros is, first of all, it's a direct method. It goes from the ODE to the solution. And what I like about this is it's super elegant. So there's at no point did we say, let's guess our solution is of a certain form. We literally went from the ODE to the solution. And another reason I like it is because people are generally accustomed to ODEs being very static. Like, this is the equation and we have the solution, but it really highlights the dynamic point of view. So differentiating is really an action that we're doing to the function. And this is sort of encompassed in that differential operators point of view. And as I said, pedagogically, it's very nice because in the chapter on first order ODEs, it's very elegant where you just go from the ODE to the solutions, and students are usually very confused when you go to the second order ODEs and you do guessing, but this is not the case anymore. And mathematically, for me, it's interesting because that's one way of proving uniqueness, because you really go from the ODE to the solution. Now, that's all and well. Of course, there are cons as well. First of all, it eliminates the discussion of Wronskian, which, as much as students hate it, it is a very useful concept. And in particular, there's no discussion of linear independence of solutions, which again is useful, but in my opinion, more appropriate for linear algebra and differential equations course, to be honest. And also, it's hard to generalize this to variable coefficients, but I mean, so is the guessing part, to be honest. And as you'll see, even though the repeated roots case will be super elegant as well, the complex roots case is very awkward. Okay. And as promised, what makes a math technique so powerful is its generalizations. So in fact, let's apply this to harder cases, and you'll see we'll go very far. We'll go all the way to PDEs, believe it or not, because that method is so cool. But this does deserve a joke, though, since this is a little Zoom talk. So e to the x was walking down the street, and suddenly there's a rain of differential operators. But e to the x is like, oh, I don't care. If you differentiate me, I stay the same. And all of a sudden, there's a differential operators drop that says, aha, I'm going to differentiate. But e to the x is like, who cares? I'm e to the x. But then the differential operator is like, aha, but I'm d over dy. And e to the x is like, no, because if you differentiate e with respect to another variable, you get 0. Okay. Anyway, so let's continue. So let's do the repeated roots case. So let's do y double prime minus 4y prime plus 4y equals 0. And in fact, this is my favorite example because it explains, again, from first principle, why we have this extra t. Because I've been guilty about this. I just tell students we have this extra t because we want a harder guess. But now you can actually see it emerging from a simple integration. Okay. So let's show why we get those solutions. So once again, let's factor things out. So d squared y minus 4dy plus 4iy. This time it does become a perfect square, but not too important for us because we can just write this in terms of two things. Once again, the right-hand side, you call it z. And then we once again have a first order ODE, which we can solve. Again, so far, nothing new. So if you're bored, that's a good thing. So d prime minus y prime minus 2y equals ae to the 2t. But now, if we apply integrating factors, you'll find something different. Kind of like a resonance effect going. Because if you multiply this by e to the minus 2t, before we had the exponential term with non-zero exponent, but now precisely we get a constant. And what is the nice thing about integrating constants? You get the extra t. So you see, here's precisely where this extra t lies. And then you just multiply and you do get your solution, ae to the 2t plus be to the 2, bte to the 2t, right? So you see, once again, the main thing here is the elegance of the method. Okay. Now, as I said, this is the good part. Unfortunately, complex roots is a little bit awkward, but still direct, actually. Because once again, let's apply differential operators to it. So d squared plus 2 plus I, y equals 0. Now, we can factor this if we now go to the complex world. So d plus I minus times d minus y equals 0. So I captain. And if you do the same spiel as before, you do get this time complex exponential solutions. So still ae to the it plus be to the minus it. And just as before, we just want to write this in terms of real and imaginary parts. So unfortunately, this gets a little bit messy, but not too bad. So e to the it, e to the minus it. Well, let's write this in terms of Euler's formula. So cosine t plus I sine t, cosine minus t plus I sine minus t, which we can clean up using the laws of cosines. Okay, well, but now let's focus on the constants, because again, we want real solutions. So an a and b could a priori be complex. So let's also expand those out in terms of complex numbers. Okay. And then let's just do an expansion party because it is Sunday and expand all those out. Again, just keeping the real parts because we won't really care about the complex parts. And notice what is nice, the cosines factor out, the sines factor out. So let's do that. I know lots of algebra, but the point is then what you get is that y is in fact a real linear combination of cosines and sines plus some purely imaginary parts. And what helps us is simply that if y is a real solution, y is its real part. So the real part just becomes this cosine and sine part. And as I said, the real part is just a solution. So after some laborious work, we actually get cosine and sine. So if you want to be fully rigorous, that's how you get it. And again, again, although it's more painful, again, no guessing involved whatsoever. So that's the nice thing. So once again, we just get to the real. And as I said, this is so powerful, it even generalizes to inhomogeneous terms. So let's do an inhomogeneous equation, again, without any weird undetermined coefficient guessing or bar of par, although I do really like bar of par, but that's beside the point. So once again, factor this out, and then we get, just as before, two first order ODEs. And then the nice thing is the method doesn't become necessarily harder. In fact, it's just as hard. The only difference is, well, before we had 0 right side, but now we have non-zero right side. But again, using integrating factors, you can just solve this. So you get z prime plus z is 5e to the 4t. Again, just product rule. And then you can just solve this. So once again, you integrate, you solve for z, and then once again, you just solve for y using the definition, which again, is just an extra integrating factor term. So you get this. And again, what is nice here is, if you notice, look precisely at the previous example, and you teach it using undetermined coefficients, this is a case where there's resonance. But the nice thing is this method takes care of resonance without even thinking, because the resonance part comes in this term with 1, which when you integrate, then you directly get the extra t. So you have this t, and then you just solve for y, and you get your solution in the end as well. And by the way, I did ask this question on an exam last semester on the final, and students did surprisingly well on this. I gave them the choice between undetermined coefficient and doing it this way, and a lot of students did it this way with no problem. But once again, I can go directly to this and even explain where this t term comes from. All right. So we did scalar ODEs, and as I said, this method is so powerful, and hopefully it will change your life, but it also works for, again, non-esoteric cases, like even systems of ODEs. So take this complicated system, well, we can still apply the same technique because, well, we still have the same action of differentiating twice. And then we can, once again, just factor everything out. So d minus 2a times d minus 3ax equals 0. Once again, you let this be z, and we get a first order ODE, which is quite cool because before we had scalar exponentials, but remember for matrices, we have complex exponentials. Matrix exponentials. So we can still deal with it the same way. So e to the 2atc. And once again, just apply integrating factors again. So x prime minus 3ax is this. Okay, just multiply this. Okay, one little thing, we do have to integrate this matrix, and I checked it, and it does work, at least in the case where a is invertible. So I'm not touching the non-invertible case, but legitimately, you can show that. You can just do minus 1 over a times that. And so in particular, you can just multiply by e to the 3at. And you do get actually the same thing as before, because if c is an arbitrary constant vector, since a is invertible in this case, then you do get an arbitrary constant. And the cool thing is you get the same formula that you expect, which is harder to do by just guessing. Now, once again, I show you the good part of it. Of course, in general, this is sort of impossible to apply. I did say A has to be invertible here, but if it's not invertible, and I get looked up, you can still use the Jordan form. That's not a problem. But if you have like two different matrices here, and you had an equation like that, I don't see how you can apply it because matrix exponentials don't necessarily commute. So you can't just apply the laws of exponents as freely as I talked about. Right. But I do want to mention, if you do want to generalize this to complex numbers, there is something called matrix cosine and sine, and you can actually check that X has this form as well. Now, last but not least, the thing that actually motivated this, and actually is harder, but it explains everything here, is actually PDEs. Because, I mean, it seems I'm just doing magic, but this is a technique that's very common in PDEs, namely when you want to solve the wave equation. And in fact, it's motivated the same way with differential operators. So applying the T operator to U is UT. Same thing with applying it twice to T. And same with X. And it turns it into the factoring form. Again, very quickly. Again, and the nice thing is you can, here it's very easy to factor as two first order operations. And same thing here. Again, same steps, just more complicated notation. And what it does, it turns the second order PDE into two first order ones. So it turns it into this constant coefficient PDE, which usually in lesson 1, they teach you how to solve it. It's any function of X plus CT. And I know, might go over the top of some people's heads, but I just want to mention it is the same technique. So then we get first order PDE once again, and then you can show that the general solution is any function of X plus CT plus any function of X minus CT. So the thing that motivated this all. And the cool thing is this is called the wave equation, and it models the behavior of waves. And what is this is saying is, well, technically a wave, you can just decompose it in terms of two waves, one going to the left, one going to the right, which is this G of X minus CT and F of X plus CT. So really cool, but this is again one of the things where it's like, it comes from a complicated example, but you can generalize this for easier examples. That's why I like PDE a lot. All right, so this actually ends my talk. So if you're interested in more like math fun like that, please make sure to subscribe to my channel. And thank you very much and have a wonderful rest of your Sunday. Yes, any questions?
Yeah, it was a wonderful talk, and I like how it addressed student questions about assuming solutions. One question students would have that I don't know that it addresses or even can is what justifies the use of differential operators algebraically. And that seems to be inherent in differential operators. It is the same problem that beset Oliver Heaviside's use of differential operators and led to the Laplace transform, because then that could be shown to have a rigorous basis. So is that question here still something that kind of has to be left unanswered?
A little bit, but I like to motivate this really that differential equations, they should be seen as something more dynamic rather than static. That's one thing, because you're really acting on the functions. And I really like to think of it, I mean, especially if it's a linear algebra and differential equations course, because usually then in the first part, they learn about matrices and being more of a dynamic thing rather than just a table of numbers. And I think it justifies it very nicely here as well, because you can really think of it as an infinite dimensional analog of matrices in this case.
Okay, thank you.
Thank you. And generally, as I said, students, I used to teach it just the guessing way the first semester at Brown, and they were left very confused. but they really like this differential operators approach simply because of it's more direct in some sense. Thank you.
Did you say how many of videos and what scope they have on your channel?
Oh, thank you so much. So I have almost 1,000 videos, and they
No. Wait a minute. Do you have a life?
Alive?
Yeah. Do you have a life?
Oh, I thought you meant YouTube live.
No. I
No,
mean, that's
no, I do have a lot. Unfortunately, like recently, I haven't been around to posting much. But really, this was like the product of like 5 years of work.
I would imagine.
Yeah. But no, but it's really nice because so my channel it like ranges from calculus all the way to PDEs. So it's more like geared towards I think undergraduates from different levels. So yeah.
Wonderful, wonderful. I've looked at them. I appreciate it.
Thank you so much. Yeah. No, what I love about it, I did that like almost 5 years ago. I started doing that, and I still see people watching it. So it's like a very good investment. Yeah.
That's right.
Yeah. And really, thanks so much for inviting me. That was such a good idea.